The last section of Chapter 9 is going to be log equations and applications. And so we're going to be using all the knowledge that we have on how to solve equations to apply them to certain problem-solving situations. And to do that, we're going to be using the continuous change model, which you might remember is the PERT model. So a lot of these problems we'll use the PERT model for. Now, we may also use some other interest formulas that you have on a note card. When we want to use the continuous change model, that means we're going to be working a lot with E and natural logs. We're also going to use the ideal problem-solving model. If you haven't done that for a while, or maybe you've never done it because you haven't had a math teacher that's worked on that, then this will be a model for a way to organize ourselves so that we can work on getting the solution to the problem. There's going to be a lot of productive struggling in this particular unit. Okay? We're going to use this ideal problem-solving model so that we can figure out what we know and what that can help us find, then that can help us get an equation so that we can then solve the problem. So I'll be very strict about the ideal problem-solving model in that you use it, and you'll need to identify all the parts of the model as you go. And we'll also be doing all the conventions that go with it, like writing things in questions and writing complete sentences and labeling and so on. So I'll kind of explain the ideal problem-solving model as we work through this first problem. The first problem says the population of the United States reached 250 million in 1990 and was growing at about 1.0%, I don't know how to see that, per year. The Census Bureau estimated that the 300 millionth American was born at approximately 7:46 a.m. Eastern Time on October 18, 2006. We want to know what was the actual growth rate from 1990 to 2006, and then we want to estimate the population for this year. Okay, so we actually have two questions that we want to answer. Here's one of them, finding the growth rate. Then after we get that done, we want to estimate the population for this year. That's a whole other question, isn't it? Okay? So we're going to do a couple of things here. All right, I'm going to kind of split the paper here, and I'm going to start with the I for ideal. The first letter of ideal stands for we're supposed to write down what the question is. Identify what the question is. So the first thing I need to know, and we're going to write this in the form of a question so that we can answer that question. We want to know what was the actual growth rate from 1990 to 2006. Okay, that's what we want to know. The D part of ideal tells us that we are going to define all the things that we know. So if we're using the continuous change model, and population is continuously changing, that is this model. In this model, there are four variables, A, P, R, and T. If we're going to solve a PERT problem, we need to know 3 out of those 4. 3 out of those 4. So what we're going to do is we're going to write down A, P, R, and T, and we're going to fill in all the ones that we know. All right? We know that the population started at 250 million in 1990. So that was the initial amount of population. Now I can write that 250, or I could put it as a bunch of zeros behind it if I want to, but it's okay if I just leave it because the next one I'm going to put in here is 300, and that's also in millions. So if I added all those extra, or fixed all those extra zeros on there, I'd wind up canceling them out anyway. Okay, and they're saying that the amount of time that has elapsed from 1990 to 2006 should be 16 years. Okay, now you think you might already know the rate, and you might want to use this, but they're wanting to know the actual growth rate. So this is actually the variable in our problem, and this is going to be the rate of growth from 1990 to 2006, the actual rate of growth, which I don't need a question mark on it. Okay, now I'm ready to do the E of ideal. The E of ideal is to write an equation. So I'm going to fill in my PERT equation. I'm going to say 300 equals 250 E to the R times T. So I'm going to write that as 16R 16r. And now I want to solve this. So the A part is act on your equation by solving and checking. To solve this, I would first divide by 250. And 300 divided by 250 is going to give me 1.2. So I'm going to say 1.2 equals e to the 16r. I could show you that on the calculator if you don't believe me. It's 300 divided by 250. That would give me 1.2. Okay? Now, in order to solve this, I need to take the natural log of both sides. So I'm going to have the natural log of 1.2 is equal to, when I take the natural log on this side, I'm going to jump this to the front and say 16r times the natural log of e. What do we know the natural log of e to be? The natural log base e of e to the first is 1. So I'm going to just wipe that off there because that's going to be 1 times my product. Divide both sides by 16. Okay, so I'm kind of running out of room here, so I'm going to put my L up here, and I'm going to say the actual growth rate was, and this is the exact amount, okay? That's the exact amount. So I'm going to probably want to get that as a decimal. So I'm going to take the natural log of 1.2 and divide by 16. I'm just going to see what that is. Okay, and then if I wanted to make it into a percent, I'm going to go ahead and multiply it times 100. So I'm going to say that it's more like about 1.139 or 1395. That might be more accurate. 1.1395%. So was approximately 1.1. Did I say 1.3? I did. No, 1395%. Period on the end. Okay? So that's what the actual rate was more like. Alright? Now it says we want to estimate the population for this year. Okay, so we have a lot of room here, so I'm going to start another ideal here. I want to estimate the population for this year. So, I don't like this so messy, but I guess I'll write it underneath here. So here's my other question. What is the population estimate for this year? Alright, A, P, R, and T. Okay, A, P, R, and T. So let's start at the most recent amount of people that, well, let's start back here at 250 million people. We'll start at 250 million people. We don't know how many people we have right now. Okay, so A is going to be the amount of population in 2013, right? Okay, for the rate, we're going to use the natural log of 1.2 divided by 16. I'm going to use that over here, because that's the actual rate for that time span. And then the time, okay, if I'm going to go from 2013 to 1990, how many years have elapsed? Well, the number of years that would have elapsed would be 23, right? 23? Okay. Now, come over here. I'll keep going. Okay, so my equation is going to look like a PERT equation. A equals P E caret natural log of 1.2 divided by 16 times 23. Okay, my A part is to act on that equation by solving and checking. In my calculator, I'm going to type in 250 e to the natural log of 1.2 divided by 16. Now that's going to give me a lot more exact than this rounded off amount that I had up here. Okay, times 23 years. Okay, and so this tells me that A is about, okay, 324.9099. They were going to the nearest, I don't know if it's million or so, but we'll go 324 point, what do you want to say, 324.9, would that be good enough? Okay, let's go 324.9. Let's say A is about 324.9 million people. Okay, so remember our answer was 324.9099788. Okay, so about 324.9 million people. Okay, so then we would say the population estimate I want to complete this sentence up here. Complete the loop by answering this question. The population estimate for 2013 is approximately 324.9 million people. Capital letter here, punctuation on the end here. Okay, now I thought it might be fun for you to see what it really is. So there's a little website that you can go to. It's called census.gov/population, and then it's a clock. And so I've got this loaded up here. And so here it is for the day I'm making this video, which is on 2/21/13 in the middle of a snowstorm here. And it's at 1952, so that means the time is what? It would be about 8 minutes until 8 minutes until 2 in the afternoon. So it says the actual population, according to the Census Bureau, is 315,370,136. And then you can see here that a birth about every 8 seconds, a death about every 12 seconds, an international immigrant, we met one of those every 36 seconds, and the net gain of one person then is every 15 seconds. So you could figure that out over the course of a year. About every 15 seconds we have a net gain of one person. So our estimate, which was 320, let's get my calculator up here. Our estimate was 324,000 or 324,900,000 is off, isn't it? Okay. So apparently there was more of a birth rate going on for a while, but things have slowed down a little bit. Now, that's a pretty far-reaching estimate because that's over a length of 23 years, and that's pretty far to be extrapolating out 23 years past that particular growth rate. And we know a lot of things have gone on with the economy in the past few years. There's been a slowing of the economy that started around 2008, and so birth rates have been down since then because, quite honestly, babies are very expensive. And so we might say that there's been a contribution of earlier detection of diseases and better medical help for people, and so that the death rate may have slowed down as well. And so we're a little bit behind. We're about 9 million people behind what this estimate would be, what it actually is. And so it just goes to prove to you that extrapolating that far out using that growth rate probably is pretty risky business. Okay. Next question says, what rate to the nearest tenth would yield $5,800 if $4,000 is invested for 8 years? Use ideal. Okay, so what is it we're wanting to know? We want to know the rate to the nearest tenth, don't we? We want to know the rate to the nearest tenth. So we want to know what rate to the nearest tenth, and that would be of a percent, right? Would be needed to yield $5,800 if $4,000 is invested at, 8 years. Okay? Alright. Well, that's a pretty normal question. What rate would we need? So we're defining what we know using the continuous change model. A, P, R, and P. We want to start out with $4,000. We want to change that into $5,800. We want to do that in 8 years. So the R, when we're defining what we know and we're identifying what we don't know, R is going to be the rate needed. Okay, that's going to be the rate needed. Okay, since I'm writing so big. So I'm going to put my E over here. I'm going to take A equals T E to the RT, and we're going to substitute into that equation. So we're going to say 5,800 equals 4,000 E to the 8R. Okay, now I'm going to do part A. We're going to solve this. We need to divide both sides by 4,000 first. Okay, so I need to know what 5,800 divided by 4,000 is. And it is 1.45. Since we have natural logs, base E is natural log, we're going to natural log both sides. So the natural log of 1.45, we're going to jump this to the front and say it's 8 times R times the natural log of E. What is the natural log of E? The natural log of E is 1. We'll divide both sides by 8. And so we know that the rate has to be the natural log of 1.45 divided by 8. Now we are not going to go in the bank and say, okay, we need a rate of natural log of 1.45 divided by 8. Let's figure out what this should be. So we're going to go natural log 1.45 divided by 8. Okay, let's multiply that times 100. Okay, whoops, I'll leave that up here so I can see it. It says I'm going to need 4, so I rounded it to the nearest tenth. I'm going to write down my numbers. 4 point, let me write it all down here. I've multiplied this times 100, by the way, to get this rate to be 4.6445. 4446. Let me see if I got that right. Did I get it all written down? 6445444. Oh, and I put a 6 and there's a 55 on the end. Okay. Now, pure rounding mathematically, pure mathematical rounding would yield 4.6%, right? 4.6%. If we just said, okay, look at this digit, it's not 5 or bigger, but let's see what would happen with our money. If we took $4,000 and we said we're going to invest that, oops, I don't want 10 to the x, I want e to the x. E to the x, rate times time, and we said, okay, 0.046 using 4.6% for 8 years, would we get $5,800? The answer is no. We only have $5,779.37, right? So that's not enough. So when you think about this problem, this is a real-life problem. We actually need all of these decimal places out here to help us pump this up so that we can get up to our $5,800. So we wouldn't be able to use that. We'd have to round up to 4.7%. And would this be an approximation? No, it would not be. You'd have to go to the bank or wherever you're going to invest your money and you have to say, I need at least 4.7%. So when we answer the question, what rate to the nearest tenth of a percent would be needed to yield this amount in 8 years? We would say the rate must be at least 4.7%. The rate must be at least 4.7%, not approximately, but at least. Because remember when we did 4.6%, we said we only had $5,779.37. That yielded $5,779.37. If we bump it up to 4.7%, by knowing that I'm going to need all of this extra help from these decimal places out here, let's see if we would have enough money to change that to 4.7%. We would, because now we would have $5,825.79. So this yields $5,825.79. So you're really going to have to think this through, because this is where that thinking component comes in. If I just simply do rounding and not in the context of the problem, then I would round to 4.6%. But because of the context of the problem saying I need to have this much money when I'm done, then I'm going to have to try out my answer and I'm going to have to see what I get. Okay, we have a sample of radioactive material that has a half-life of about 1,400 years. An initial sample weighs about 6 grams. We want to find a model for the decay function for this material. Then we find the amount left after 4,200 years and how long it would take to decay to 1.5 grams. So this is actually asking us several questions, and we can put them all in the eye if you want to for ideal. Okay, so the first thing we want to do is it says we want to find a model for the decay function. Okay, so we want to know what is the model for the decay function. Okay, the next question would be, how much is left after 4,200 years? And then we want to know how long will it take 6 grams to decay to 1.5 grams. Okay, well we can answer these last two questions after we get the model figured out, right? Okay, continuous change model again, right? A, P, R, and T. Alright, so what do we know? We know that the half-life is about 1,400 years. Is that what we know? Half-life, and if you understand what half-life means, that means that after 1,400 years, no matter what amount you started with, after 1,400 years you would have half of it remaining. And then in another 1,400 years you'd have another half remaining. So let's say you started with 12 grams. Then in 1,400 years, 12 grams was at time 0. Then after 1,400 years, you would have 6 grams left. And then at another 1,400 years, so at 2,800 years, then you'd have 3 grams left. And so on and so on. Alright? So in our problem, what we know is that the time of a half-life is 1,400 years. And whatever amount you start with, you're going to have half of that remaining. So we had an initial sample. Initial means I'm beginning with that. Initially we had 6 grams. After 1,400 years, we would have 3 grams, wouldn't we? So then this would be the rate of decay. The rate of decay. And so now we want to come up with the model for any amount that would be left. Okay? So we're going to take this information and we're going to write our equation. Okay, and our equation is going to say I have 3 grams left after starting with 6 grams e to the 1,400 r. Okay, because I need to know what the rate is. Okay, I'm going to divide by 6. This should not be shocking to you that we're going to have a half. And now I'm going to natural log both sides. Natural log of e is 1. I'm going to divide by 1,400. Okay, so this is what I know. I know that the rate is the natural log of 0.5 divided by 1,400. Okay, so now I'm going to start my L process by telling what my model is for my function. My function is the amount left at any time t. I want to be able to determine the amount left at any time t. And so I really want to write this so that I can plug in any number of years. So I'm going to say that I'm starting with P, E to the RT, aren't I? So T being my variable, my independent variable. So my amount left at any time T would be 6 grams E to now my rate, which is natural log of 0.5 divided by 1400 times T. Okay? So we could say the model for the function is the amount left at any time T is 6e to the natural log of 0.5 divided by 1400 times T. So there's my model. That's how I want to model that. Okay. Furthermore, how much is left after 4,200 years? Okay. So now I want to know the amount after 4,200 years. I want to plug in 4,200 for time. So that would be 6e to the natural log of 0.5, oops, I'm placing one up, divided by 1400 times 4,200. So let's see what that would give me. So I would have 6 e to the natural log of a half divided by 1400, so that's the rate, times 4,200. So that's going to give me 0.75. So the amount after 4,200 years is 3/4 or 0.75 grams. Okay, so that answers the second question. Okay, so over here I would say the amount left after 4,200 years is 7,500 of a gram. Okay, we want to know how long it would take the 6 grams to decay to 1.5 grams. Okay, so I'm going to go back to my model here. So let's use this model. We can use whichever one of these we want. We want to decay to 1.5 grams. So we want to say 1.5 grams equals the 6 initial grams E to the natural log of 0.5 divided by 1400 times T. So we want to solve this for time. So we're going to divide both sides by 6. Do you know what 1.5 divided by 6 is? Whoops, let's get rid of that. Okay, so it's 0.25, right? 0.25. So we're going to say 0.25 equals E to the natural log of 0.5 divided by 1400 times T. Okay. Next, we're going to natural log both sides. So, here. The natural log of 0.25 is equal to, jump this whole thing to the front, the natural log of 0.5 divided by 1400 times T times the natural log of E. Natural log of E wipes out of here. And so now I need to get rid of this. I'm going to multiply by the reciprocal. The reciprocal is 1400 divided by the natural log of 0.5. Okay, so get rid of that. So my time will be 1400 times the natural log of 0.25 divided by the natural log of 0.5. I'm going to do that on my calculator. 1400 times the natural log of 0.25 divided by the natural log of 0.5. That's going to give me 2,800. So then I would say, to answer that question in a complete sentence, I'll write this one. It would take 2,800 years for 6 grams to decay to 1.5 grams. Okay. So that problem was pretty loaded with questions, but you have to take what you know and you have to form the equations to get the model, and then you can use the model to answer pretty much anything. Okay, one more example that I want to show you before I'm going to turn you loose. Okay, and this one has to do with carbon-14 dating. I don't know if you're familiar with the idea of carbon-14 dating, but carbon-14 dating is used to age things. So if you have an old painting, or an archaeologist would find something very old, they would use carbon-14 dating to figure out how old it really is. And if they can figure out what era it came from, then they could determine, if it's been painted by a famous painter, or if it's, from a the Mayan ruins or something in Egypt in the pyramids, something like that. Okay, so it says, assuming carbon-14 has a half-life of 5,730 years, give the approximate age of a skull found by an archaeologist if the skull has 63% of the original carbon-14 concentration. It's supposed to use ideal for this. Okay, so what's the question really asking us? It says, give the approximate age of the skull found by the archaeologist, right? So this is what we know, or what we want to know. Okay. What is the approximate age, right, of a skull that has 63% of its original carbon-14 concentration? That's the question mark on there. Okay, now I'm going to start with this, because we always start with this, and then I want to talk to you about how this problem is different than the other problems that we've been doing. In this case, this amount of time is the half-life, which goes with 50% left. Okay? We have 63% left, don't we? So if I use the time of 5,730, then it goes with an A and a P that are half of each other. And it didn't tell me anything about the number of, how much concentration or whatever. Well, it's not going to, because when the person died, whoever's skull this is, I don't know if it's the skull of a person or an animal or whatever, it had 100% of its concentration, and then it continually is losing and losing and losing. So it starts with a P of 1. 100% would be 1. This amount of time right here would make this go to 1/2, or 0.5, not to 63%. That's a different problem. Okay? So we have to figure out the rate at which it's losing its carbon, the half-life rate. Then once we figure that out, we can go back and use this as our amount. This will be our A. And so we're really going to do an I, D, E, A, and then a D, E, A, and then an L. Because we've got to figure out the rate. First of all, we'll use this to figure out the rate at which it's decaying, and then we'll come back and we'll do another one of these to figure out the answer to the question. Alright, so my equation is going to look like this. It's going to say I would have half left after starting with 100% e to the 5730 r. Well, dividing by 1 on both sides doesn't do anything. Just gets rid of that 1. And so it's the natural log of 0.5 is equal to 5730 r times the natural log of e. And so I'm going to divide by 5730. And so this half-life rate here is the natural log of 0.5 divided by 5730. Okay, so that's what we figured out. Now, let's come over here and apply it to the amounts in the problem. Okay, my question is the approximate age, so this is what I don't know. This is what I don't know, the time. This is the approximate age, right? How long it's been decaying. The rate is going to be the natural log of 0.5 divided by 5730. When I start with 100% and I end with 63%. So you see how the 63% doesn't go with the 5730? Okay, now I'm going to make an equation. And I'm going to say I have 63% left after starting with 100% of e raised to the natural log of 0.5 divided by 5730 times t. I'm going to divide both sides by 1, which is just going to get rid of this. And then I'm going to say that I have 0.63 equals e to the natural log of 0.5 divided by 5730 times t. Now I'm going to take the natural log on both sides. Jump this to the front. The natural log of 0.5 divided by 5730 times t times the natural log of e. The natural log of e is 1, so I'm going to multiply both sides by this reciprocal. 5730 over the natural log of 0.5. Okay, so the time that I'm going to get on my calculator is 5730 times the natural log of 0.63 divided by the natural log of a half. So 3,819.48. Now I don't know how specific you want to get when you're trying to figure out how old the skull is. It's in the thousands of years, so we could say about 3,819 years. Would that be okay with everybody? I think so. We'll try that. 3,819 years. Okay, so then for our L, we're going to say the skull is approximately 3,819 years old. Okay? Notice I have capital letter, period on the end. I had a capital letter here with a question mark for my question. So this one was kind of a souped up, super duper ideal problem in that we had to take the information with this number and compute what the half-life rate was. Because I need that rate then to write this as a function of time, because I really wanted to solve for the age of the skull. Well, 5,730 is an amount of years, but it's not the age of the skull. That's the amount of time in one half-life. So that becomes kind of a complicated problem. You will run into some problems that you have to do this with, but I think you'll notice them when you see them. So what are you going to do for homework? Well, you're going to do these ideal problems, and then you've got some more over here. So you've got 8 ideal problems that you're going to have to do. Some of them, if you want to survey them and look at them, some of them are going to be easier than others. Some of them are straight ideal. They're just straight ideal. If you know the rate for carbon-14 dating, we just figured that out right here, didn't we? This rate will be always the rate for carbon-14. So any problem that you have that has carbon-14 in it, you don't have to re-find that rate. You can use it. So here's a problem that has carbon-14 dating in it. Here's a problem that has carbon-14 dating. You wouldn't have to do an IDEA, DEAL, because you can skip the first DEA there if you use the rate that you found up above, and I would believe that you could do that. Okay? Now, when you get down to number 3, you'll see that you have a different rate going on. It's not carbon-14 anymore. Okay? Number 4 is an interest problem. We did one like that on the front page, so be sure you double check and make sure your interest rate is high enough for that problem. And then you've got some more over here to do, and these will all be ideal problems with the continuous change model. Beyond that, you're going to solve some more log equations because we need some more practice on those. So again, think about the 3 different types, the triangle, the circle, and the star, if you can do those. And then you've got some exponent problems at the end. If you have any trouble with this at all, and this might throw you some curveballs, you can come and see me. I'm not probably going to help you find the answer as much as I'm going to help you think about what questions you should ask yourself. This is a great lesson on productive struggling.